Hey, this is Horner, and this is the second part of the rotational motion unit for AP Physics 1 and how to be successful on the AP Physics 1 test. The rotational kinematic equations are exactly like the translational ones, except for instead of using like v for velocity, we're going to use omega, which is angular frequency or angular speed. Here we've got position. Remember, that's the angle. Velocity is omega, and then A is going to be alpha for rotational. So all of these equations are exactly the same as what we've remembered from before. You just have to make your mind think, oh, if it's turning in a circle, I have to use these. If it's going along a straight line, I can use these. And if I want to switch between the two, I just need to know, I need to multiply whatever the rotational is times the radius, because the radius is the thing that helps us remember that it's going in a circle or doing the rotational motion. So at this point, we're going to try some problems. We have a carpenter who's cutting a piece of wood with a high-powered circular saw. The saw blade accelerates from rest, so we know that our original our original omega, so our original speed here, angular speed, is 0 radians per second. And it says that it goes all the way up to 15,000, so that would be our final speed, so 15,000 revolutions per second. So this is in revolutions, this is in radians. We need them to be in the same thing, so we're going to need to convert here in just a second. Says what is the maximum speed of the saw in radians per second? So that's the first thing we're going to do, is find the maximum speed of the saw. We know that it is in 15,000 revolutions per second. We need to turn that into radians per second. So there are 2 pi radians in every 1 revolution. And at this point we can solve, and we end up with 1,570 radians per second. So pretty simple to do. Now they want to know how long does it take. So how long is time to reach its maximum speed? We're going to use the first kinematics equation for rotational motion. So that's the angular final speed is equal to the original angular speed plus alpha times time. We can then rearrange this for time. So we're going to take the final speed minus the original speed. We're going to divide that by alpha, and that should be equal to time. So now we plug everything in. 1570 minus 0 all over, and then they told us it was 14 radians per second, so this is 14 radians per second squared, and when you're done you should get 112 seconds. The last question that's on this one wants to know how many complete rotations does it take for the saw to make while it's accelerating to the maximum speed. And so at that point we know we want the change in the number of rotations, or the angle here is related to that. So that's the original speed times time plus 1/2 of the acceleration times time squared. So we're going to plug everything in here now. We're going to do, this original speed was 0, so this thing just goes to 0, and we're left with 1/2 of the acceleration, which is 14, times the time that we got, which was 112 seconds squared. And so here we end up with 87,800, but that's radians. So because we have radians, we need to convert the radians on over to revolutions. And so there are 2 pi radians in 1 revolution. And at that point, when you divide the 2 and then divide by 2 and then divide by pi, you should get 14,000 revolutions. And that's number 12. For the next part, which is number 13, so this is a multi-step problem here, just like you would see on the AP test. Safety mechanism will bring the saw blade to rest in 0.3 seconds should the carpenter's hand come off the saw controls. So they want to know what is the angular acceleration that this requires, and then how many complete revolutions will the saw blade make in this time. So let's go ahead and do that. We're going to first find out what the acceleration is. So I'm going to switch to a better pencil here. This is the final velocity is equal to the original velocity plus the acceleration times time, or angular speed and angular speed and angular acceleration. So here is our angular acceleration is just the difference in those divided by the time. This will be, remember our final speed is 0, original speed is 1570. We're going to divide that by the time, and we end up with an angular acceleration of negative 5,230 radians per second. Next thing they want us to find is how many complete revolutions. So we're actually looking for the change in the angle here, and that should be equal to omega t plus 1/2 alpha t squared. We do know that we had 1,570 radians per second. That happened for 0.3 seconds. Plus 1/2 of, now here's where we put in our angular acceleration, negative 5230 radians per second times 0.3 seconds squared. And we end up with a change of 236 radians. So we want to know how many revolutions does it make? And so let's go ahead and do that. 236, this should be radians, sorry. So 236 radians. We want to know how many, let's make it radians. We want to know how many revolutions that would be. So one revolution we know is 2 pi radians. And if you do that, you get 37.5 revolutions. So it's still going to spin 37.5 times. So that's a lot. So probably still do damage, but probably won't do enough damage to be really, really bad, I guess. Alrighty, so let's go ahead and take a look at the next one. This one says we have an amusement park ride of radius x, allows children to sit in a swing, and they're held by a cable of length L. So they want us to go through with this one, and they want us, if we know the maximum angular speed the cable makes, an angle of theta with the vertical as shown in the diagram below, they want us to find the maximum angular speed of the rider in terms of g, theta, x, and L. So this is a typical AP problem where they're going to go through and try to get you to do everything just in terms of letters. So let's start this one by looking at kind of what's going on here. We've got this thing turning in a circle, and it does that. It then has this rider kind of swinging out at this angle. So let's go ahead and think about all of the forces. We need to do a sum of the forces in the x direction, and we need to do a sum of the forces in the y direction. So the sum of the forces in the x direction, because it's going in a circle, we know that this person's getting pulled in towards the center of the circle, and therefore that would be mass times centripetal acceleration. And in the y direction, we're just worried about going up and down, and notice this person is not going up and down, and so the sum of the forces in the y direction is 0. Let's go ahead and think about all of the forces on this person. So let's do a free body diagram. Let's just put it right here. And we know that we have a force going up this way, that is tension. And we know we have a force going down in this direction, and that is the person's weight. We want everything to be in the up and down direction. So let's go ahead and let's make x and y components for this. And so here's our angle theta. Now notice that they gave us this angle right here. So actually these two angles are the same because they are on opposite sides. So we're going to stick with this triangle. This side would be t times the cosine of the angle, and then the top side here would be t sine of the angle. Awesome. So now we've got all those things. Let's go ahead and look at what's in the x direction. So in the x direction here, we're going to have only one thing. That's going to be t times the sine of the angle. And that's going to be equal to, remember, centripetal acceleration is mv squared all over r. So lots of things that you have to go back and review, hence why this is the last topic we do right before the test. Now that we kind of know what t sine of the angle is, let's go over here and let's do the other side. So some of the forces in the y direction are equal to 0. So that's going to be t cosine of the angle, since up is positive, minus mg is equal to 0. So t cosine of the angle is equal to mg. Let's go ahead and let's solve this one for t. So we're going to say t is equal to mg over the cosine of the angle. And now we're going to take this t and we're going to plug it in over here for this t. So let's go ahead and switch colors. I think that'll help us a little bit as we go through. And so now we're going to have mg times the sine of the angle over the cosine of the angle, and that should be equal to mv squared all over r. Sine over cosine is tangent. We can also cross off our masses. So here our masses, don't worry, don't matter. So that would be tangent of the angle. We're going to divide both sides by g is equal to v squared over g times r. So now we have a good way of looking at kind of what's going on in the circle. We do want to make sure that we're trying to find out what is the angular speed. So they want us to find angular speed. Right now we don't have angular speed. So this thing right here, remember, is linear speed. And linear speed is equal to omega times r. So what we're going to do is take, see how this is squared, we need to square this, and so if we square it, we're going to get omega squared r. So let's plug that in here. So this is tangent of the angle is equal to omega squared times r squared. So we're going to get omega squared times r squared all over g times r. At this point we see that one of the r's cancels on the bottom, one on the top. And so now we're left with tangent of the angle is equal to omega squared r over g. We want to solve this for omega squared, so we're going to say omega squared is equal to g times the tangent of the angle all over r. Now we need to do the square root. So now we're going to do omega is equal to the square root of g times the tangent of the angle all over r. The last thing that we have to do is it does not say that we can use r. So we've got to figure out how do we relate r and L? How do we relate r and L? So to do that, what we can do is we can say that r here, so the radius r should be equal to, and then we're going to take x plus L times the cosine of the angle. So we want this distance right here on the bottom of this triangle plus the distance to the center. So this is x, that's really easy. This side we've got to do L times, oops, sorry, it's not cosine, this is actually sine now that I look at it. So let's switch over to our eraser and let's put in sine. So this is L times the sine of the angle. So this is L, this is the angle, so this side would be L sine of the angle. All right, so our final answer, let's go ahead and do this in purple. We're going to substitute the r for x plus L sine of the angle. So now we're going to end up with our final answer, omega is equal to the square root of g times the tangent of the angle all over, and then we're going to do x plus L sine of the angle. And so now we are finished with that rather more difficult problem. Let's go ahead and look at the next slide very quickly. And on this next slide, this just gives us all of the things we've talked about where we know that if we want the change in position, so this would also be equal to distance if you wanted it to, or the change in x, that's equal to in rotary motion or in rotational motion, it's just the difference in the angles. And then you see all of our equations all the way down and how they all work. So basically same equations, but if we're going to go from one thing to the other, it's always the bridge is always our radius. And I think what we'll do is this will be the end of this video, and we'll go on to the next one.